So I'm going to talk about applications of reflection in Agda. And this is joint work with my master's student, Walt. He's finishing up his master's thesis in Utrecht at the moment. And what he's worked on really is Agda has this new reflection API. So Agda is a functional programming language with dependent types. We saw it on Cesari's slides a little bit. And since version 2.2.8, which is quite recent, Agda has what's called a reflection API. So you can think of things like template Haskell if you're a Haskell programmer, or quote eval if you're a scheme programmer, that kind of reflection. And his thesis is all about trying to have some fun with this feature and then see what we can do that we couldn't do before. So the reflection API, it looks something like this. You don't have to understand all this slide. But basically, it exposes a data type for terms, where terms can be things like lambdas or pies, or they might be constructors or sorts like set or set1, set2, or so forth. Or it might be unknown because there might be holes in your program somehow. And in addition to exposing a type like this, you have various ways to get your hands on the abstract syntax tree for a piece of concrete syntax, or to splice back a generated term or a manipulated term and get that back into code in your program text. So what we've been doing is trying to find some nice applications of this technology. So I'm going to talk about a few today, the first two, and then I'll say something towards the end about the other things you could use this for. So proof by reflection, metaprogramming, generic programming, and program transformation. Okay, so here's an example taken from Adam Safala's Certified Programming Independent Type. So that uses prompt, but now we'll use Agda. So suppose you have a type of natural numbers, and you have a predicate on natural numbers defined as a data type, saying exactly when the natural numbers are even. And there are two constructors. One says 0 is an even number, the other one says if you have a proof that n is even, then you can use the step constructor to build a new proof that n plus 2 is even. Now, if you want to prove that 1024 is even, how do you go about doing this? Well, the dumb approach is copy-paste, and then find the right number, exactly the right number of step cases, and finish off with the base case. Or you use Emacs macros to generate this kind of thing for you. But that gets dull very quickly. So the not-so-dumb approach is to do something a little bit more clever. And what you actually do is you write another function, which I'll call even question mark, which any natural number computes a set. So the important thing is that you make the distinction between an inductively defined predicate and a function which computes. So here we have another definition of the even predicate, but now it's defined as a function. And we say that, well, 0 is always even, and the proof that we need for that is just the unit type. And if we try to prove that 1 is even, we need to have an inhabitant of the empty type. So it's another way of saying that 1 is odd. And then the final case says that if we have a successor of a number, and we want to know if it's even or not, we just make a recursive call on it. So the key thing which makes all this work is that this function computes. Given a number, it will immediately return either unit or empty. Now what we can show is that if we have a proof that n is even, then we can actually construct one of these inductively defined data types showing that the number n is even. So there's one or two tricks which are a little bit important here. I've made the even argument here implicit, which means when I call sounders, I don't need to pass in the unit type explicitly. So here what you see is that if to prove that 0 is even, we use the base constructor. To prove that the successor number is even, we use step and then make a recursive call. And in this case, if we need to show that 1 is even, this type is uninhabited. And this is just some Agda notation to show that I don't need to give a right-hand side of this definition because there's no way anyone can ever pass the argument of the empty type. So essentially this shows that if we want to construct an inhabitant, the inductive thing, it's not to have an inhabitant of the proof that even question mark is inhabited. But the good thing is that proving that even question mark is inhabited is really easy because that just computes. So now to prove that 1024 is even, all we need to do is we call our sounders function with 1024. There's a little bit of computation going on, and then that turns out that to call this function, we should also pass in basically the unit type. And Agda is actually very generous here, in that if you have implicit arguments of type unit, they get filled in for you, because there's only one way that they can be filled in anyhow. So you don't need to worry about that. So this works. And if you try to prove that an odd number is even, Agda says, well, to complete this definition, I'm missing an implicit argument of type empty. So there's no way that you can produce that kind of witness. So you know that you've made a mistake. Or if you change the way the even question mark predicate is defined a little bit, you could have some kind of more informative type level error message in a way, where you just make an is not even type, which has no constructors, but is indexed by natural numbers. So then you can see that Agda will say something like, I can't figure out what implicit argument to fill in here, and it has to have type is not even 13. So that means that'll tell you that you've made a mistake somewhere. Okay. So this works quite well. And what's the general pattern that you use here is you typically start by defining some type of your problem domain. So that in our example, that was natural numbers. And then we have some predicate that we might be interested in, or some goal we're trying to prove. So that in that case, that was our even data type. And then we define the decision procedure, which is actually a function which computes and usually returns either the unit type or the empty type. And then we prove a soundness number that our decision procedure actually has the same behavior as our predicate that we're interested in. And then whenever we actually want to produce a predicate, we just call our decision procedure and the soundness number together to get the result we're interested in. So this works actually quite well. I should point out that I haven't used any of the Agda reflection API yet, but that's what I'm coming up to next. So you can do this, and there are lots of examples of doing proof by reflection. So you might want to have solve equations over some algebraic structure, like monoids or rings. Or you might have some small, simple logic which is decidable, such as positional logic or anything like that. And then you can write, in a sense, automated tactics which will generate proofs for you. So in the paper, one of the things we've looked at is a decision procedure for Boolean topologies. So I'd like to talk a little bit about that. So suppose we want to prove something like this, that for all Booleans P1, Q1, P2, Q2, this equation where these ors and ands are just the Boolean ors and ands, and the implication is the usual implication, and so it says true to the unit type and false to the end. So if you want to prove this, there are roughly two ways you can do it. You can either do pattern matching on all the Q's and P's. So in this case, you have 16 branches and have 16 unit types on the right-hand side. So that's quite dull. The other thing you could try to do is prove some laws like P implies P and how and distributes over or, and then you can rewrite all these laws until you get something which is obviously a tautology and then you're done. Neither of these, once again, are very much. So, how can we get around? So it's the same trick, basically. The only difference is now we'll define an abstract syntax tree for our Boolean expressions. So we have truth and falsehood and various logical connectives. And then we also have atomic here, which we use to represent variables. So, no surprises there. Then we can do evaluation of these things. And then we can say, given some environment, which contains the assignment for our variables, how to interpret our variables. And a Boolean expression will compute the Boolean saying whether the whole expression is true or false. And this is what does what we expect. It sends implication to the implication between Booleans and not to not to not to not, and so on. And the only slightly interesting case is for variables, you look up what they are in the environment. Okay, so far so good. The next step is that you actually generate all possible environments. So this is saying, when is this Boolean expression true under every possible environment? So if the Boolean expression has no variables in it, then we just check whether, I've done this for lower ground, sorry, it should be vexed and nil should be swapped, presumably. So if the Boolean expression holds in the empty environment, then it's unit, otherwise empty. And if we have a non-empty thing, then we should check that the Boolean expression is it holds when the variable is assigned to true and when it's assigned to false. So I should give a slight footnote, is that I've cheated a bit here. To write this function in this style in Agda, you need to do a little bit of work. Basically, it's the same problem if you've ever tried to reverse a vector in Agda, and you end up doing a little bit of arithmetic to show that n plus 0 is equal to n and that kind of thing. So you need to do something similar here. So it's not quite this tricky in real life if you look at the code. But once we have this, we can reformulate the Salinus result. And that says that if a Boolean expression holds in every environment, then that Boolean expression is necessarily a physical function. Okay, and proving this is a few lines of work, but it's not too complicated still. And then we can start thinking about how we want to call our solver. And this is where you can see that things get a little bit uglier than we have in natural language. One of the problems is here, that to call our Salinus result, we need to pass in the Boolean expression, so that's our AST thing, which represents this thing up here. So that's not so nice, because you're duplicating work. You've already written down the thing you want to prove here, so why do you need to go out and spell it out explicitly using these constructors? So from this type, we should be able to get all the information we need. And this is where the reflection comes in. So one way you can use reflection in Agda is using a keyword called quote goal. And what that tells you is it allows you to bind to a new variable the type of the current goal. So you're trying to prove something, and then this tells you this is the type of the thing you're trying to prove. And this is useful because suddenly, if we have this type as one of these terms, one of these data types that we can traverse and inspect, we can peel off all the variables, and we can look at what kind of Boolean expression is underneath, and then generate the corresponding data type that we use in our Salinus. Okay, so that looks something like this. This is all rather dull code, but you can kind of see what's going on. I don't expect you to understand this. But basically you check whether you have a constructor whose name happens to be equal to true, and if it is, you return the truth data type. And if the name of the constructor is equal to false, you return the false data type. And if it happens to be equal to or, you return an or, and so forth. And you need to carry on with recursive data. But then you can solve problems like this quite nicely. So, for example, if you want to do a proof that for every Boolean B or not B holds, how does that work? Well, calling our solver is now really easy. We quote the goal, and then we pass the raw term to our prover, which first takes this term and then inspects it and builds up this AST and then calls the Salinus result, and then there's various bits and pieces which you don't see, but kind of the interface that you get as a user, I think is really great. And once again, I'm just filling in lots of logistic arguments for us. In particular, it's filling in 2 to the nth unit types, which are passed to the Salinus result if you look for when we have an expression of n with 3 variables, or Boolean variables. Yep.
Not following very well at the moment, so quote goal compute.
Okay. So typically in the Agda style development, what you start with this definition, and then you have and the question mark here is denoting. I don't know. I haven't finished this part of my program yet.
So quote goal.
And then quote goal. If you write quote goal E in, what that will give you is that it'll bind the type of this thing to E, and then you can use that when you call prove the function.
Type of this thing is now.
So basically, E in this example is bound to this type.
Type.
Yeah, but I should say it's not bound to this in particular. It's bound to the term representation of this. So you get the constructor pi of Boolean form the bottom. Right. Okay. So a little bit of reflection. So there are some no limitations with the current implementation. So you can't access function definitions You have limited access to data type definitions, and there's no way to generate top-level definitions. So this is really quite limited. And one thing which bugs a lot of people about doing this kind of meta programming is that it's essentially untyped. You have one big type for your terms, and you can reflect into that, and then you manipulate that, and then, who knows what kind of type you end up generating. So there's a question you can ask is, can you program with reflection state? And if you've seen talks about dependent types before, you've probably seen slides like this where they define some small type language, and then they describe the data type for it, and its interpretation as a set. They might define a context to be a list of these type representations. They may define some nice type representation of lambda calculus, where you have lambdas abstract applications invariant. And you can kind of see that you should read this as saying that the application takes two type term arguments, one which has this type and one which is type u, and builds something with type. So the kind of typing rules of the simply type lambda calculus are baked into this data type. So that's really cool, but it's very hard to do this for a dependently type lambda calculus. I mean, people have tried. James Chapman has a thesis on this. Nils Anders Danielson has written about this. Colin McBride has published a way to do this. But none of the solutions are completely satisfactory. But still, you can use, if you stick to the simply type fragment, you can use these kind of data types. You just need to do a little bit more work. So I'll sketch that now. What you can do is you can take an untyped term, which you get by quoting some expression, and then you can define your own little type checker, which takes this untyped term and produces one of these typed terms. And then you can manipulate this well-typed term in a predictable way. So you can either CPS transform it or do your SKI translation. And the nice thing is that this translation works on type terms, so you can clearly see that it's type preserving, or that it generates new types in the structure. There's some drawbacks to doing things like this. Most notably, well, you need to write the type checker. That's not too hard to simplify that. But when you unquote, you throw away all your type information. If you have to unquote, you have to give one of these raw terms again, and you have to basically throw away all the fancy types you just spent so hard working to generate. So in the end, you still don't get as much type safety as you'd like, because unquote is one of these is basically an untyped keyword, and it doesn't know anything about all the hard work you've done to generate these type names. But still, it's better than nothing. So I want to say a few things about future work. So things we've been looking at is using a reflection to do kind of programming with universes, generic programming, infinite ornamentation, that kind of thing. And all of this kind of breaks a little bit because you can't splice in new functional definitions. You can't generate new data type definitions or new function definitions. So that's something we really like to fix. Another example is if you work with Agda, you know that you can only write structurally recursive functions. And if you write a function which isn't structurally recursive, but Agda marks your function as being dubious, and then you have to think about how can I change the function somehow to make the recursion more obviously structural. And there are various tricks which are well known and well documented. They're like program refactorings almost, which say, oh, you should do induction over some well-founded relation, or you have the Bove-Preti method, which introduces a new argument to your function, and it's basically a call graph of the function, and you can always be structurally recursive over that. Well, it'd be nice if these kind of things were automated, and you didn't have to do them like that. And one way to do that in a quite lightweight fashion, without having to touch the compiler or the IDE, would be using this kind of reflection. Yeah. And finally, I think there's plenty of work to do to improve the reflection API itself, because it's kind of cobbled together over the hack of the week of Agda implemented weekly. But it's not very mature yet. So part of the reason to do this project was to explore what is possible now, and what kind of extensions would you need to do the things we're having. So, okay, thank you very much for your attention.
Your questions, Bedroom?
Thanks for the talk. I've been wanting to look at the reflection API in a while, and now it's like a nice introduction. The fact that it's untyped, if you have a self-encoding universe, like in Epigram 2, this levitation stuff, wouldn't that just...
It'll get you close, but the problem is you have to get a representation of terms, not just their type.
Not just the types.
And So the reason the simply typed lambda characters work so nicely is it's completely layered. You can start by defining this is my type language, then my context of list of types, then I can define what it means for, then I can define my lambda terms, and I can define evaluation on these things. And none of these things are mutually recursive or anything like that. It's one after the other. If you do it with dependent types, suddenly your types and terms are mixed. When you try to define your term data type, you have to worry about evaluation because you have to compare whether two types are equal. So all of a sudden you get into a big mess basically, because you have to define evaluation mutually recursive with the data type you're trying to define, mutually recursive with context, mutually recursive with your type language, and so forth and so forth. And it really, so no one's come up with a good solution yet. Maybe that's it.
Okay.
Yeah.
So we're talking about error messages with the purpose. I was wondering, sort of, I imagine it gets bad, just how bad does it get if you sort of don't get the right thing out of your quote type function? Either your quote, the function you plugged in past that is wrong somehow, or you're just in the wrong place.
So typically what you can do, if you look at the example we had with quote bool, so there's a few implicit arguments which I've left out. And one of them is it inspects the term E, and then it decides whether it has the right shape to be able to be translated into one of these booleans. And if it doesn't have the right shape, so if it does have the right shape, it returns unit. If it doesn't have the right shape, it returns empty, or a variant of empty, which is tagged somehow with information about, oh, I don't know how to handle, suppose you had a NAND, right? So I don't know about NAND, so I can't translate this to a rendering-based. Okay. So there's, you have the opportunity to kind of generate your own error messages by you're basically using invented type names, which specify why something could be flipped.
What's the main difference between the Agda reflection API and the API? So an SSL reflecting COP?
Okay, so SS reflecting COP, so I'm not an expert, but it's similar. What SS reflect is all about is, as far as I understand, so once again I'm not an expert, but it's used to do this kind of proof by reflection. And most of the technology that's there is about turning Boolean decision functions into predicates and back and forth. A lot of the difference, I suppose, is that SS reflect, it doesn't give you the term data type like this. Instead, the way you usually do it in Coq is you have this LTAC little language, which allows you to kind of ask questions along the lines of, is my goal of this shape, or do I have something of this type in my context? And it's a little bit, it's not very nice to work in, but that's the way these reflection proofs are usually done in Coq. Whereas here you have the ability to more programmatically, instead of having to use a separate LTAC language, which is a little bit weird, here you can just write a traversal with terms and then inspect terms to see whether they have the right shape or how you want to manipulate them. Yeah.
Okay, thank you.
Thank you very much.